Welcome to this HPC Practical walkthrough for SPPUB E Computer Science Semester 8. In this video, we cover Practical 1 and Practical 2, both using OpenMP for parallel computing in C++. No special installation is needed, just use Jupyter or VS Code with a G++ compiler that supports OpenMP. OpenMP is built into GCC, so no separate installation is needed. You just need the right compiler. On Windows, install mingw w64 via msys2. Open the msys2 mingw terminal and run the following command. Once done, follow installation procedure as shown on the site from point 6. In VS Code, install the C++ extension by Microsoft. That's all the setup you need. OpenMP support is activated at compile time using the fopenmp flag. No extra library installs required. Practical 1. Parallel BFS and DFS using OpenMP. We have an undirected graph stored as an adjacency list. The graph class holds vertices and edges. Add edge connects two nodes in both directions, making it undirected. Before we dive in, OpenMP works through pragma-omp directives. These are instructions you give the CPU, telling it which parts of the code can run simultaneously and which parts need to wait their turn. In parallel BFS, we start from a source node and mark it visited. At each level, we use pragma-omp parallel for this splits the current queue's nodes across multiple threads, so all of them are processed at the same time instead of one by one. But since multiple threads share the same queue and visited array, we wrap those accesses in pragma-omp critical, meaning only one thread can modify them at a time. This prevents race conditions. In parallel DFS, we use pragma omp parallel to create a team of threads and pragma omp single to make sure only one thread starts the recursion. For each unvisited neighbor, we use pragma omp task. This packages each recursive call as a task that any free thread can pick up and execute. Again, a critical section guards the visited array. In main, we take user input for vertices, edges, and the starting node, then call parallel BFS and parallel DFS and print the traversal order. Practical 2, parallel bubble sort and merge sort using OpenMP. We work on a randomly generated array of 10,000 integers. Sequential bubble sort does a standard nested loop comparison slow O(n) squared. Parallel bubble sort uses the odd-even transposition technique. In the even phase, we compare pairs at positions 0 to 1, 2 to 3, 4 to 5, and so on, all in parallel using pragma p parallel for just like we saw in practical 1. In the odd phase, we compare pairs at positions 1 to 2, 3 to 4, 5 to 6, again in parallel. By alternating phases, adjacent elements never conflict, so parallelism is safe without needing a critical section. Sequential merge sort is the standard recursive divide and conquer approach. Parallel merge sort introduces two new directives, pragma omp parallel sections divides the code into independent blocks, and pragma omp section marks each block. One thread sorts the left half, another sorts the right half simultaneously. A depth parameter controls how deep this splitting goes. Once it hits 0, it falls back to sequential sort to avoid creating too many threads unnecessarily. In main, we use omp getWtime to record timestamps before and after each sort, giving us clean comparison of sequential versus parallel performance. Looking at the results, bubble sort shows minimal speedup due to high synchronization overhead. Merge sort shows a clear improvement. Parallel version is faster because the two halves are independent. This demonstrates a key principle: parallelism helps most when tasks don't share data. That's it for practicals 1 and 2. In the next video, we move to GPU programming with CUDA on Google Colab.